Yes, welcome everyone. My name is Arya Hakimian. Welcome to today's guest webinar titled Thermal Conductivity Testing of Pressure-Sensitive Adhesives for EV Systems. Guest webinar here today, so I will be joined a little later on in the presentation by Matt Gray, who's a senior product development chemist from Adhesives Research Inc. So today's session is going to kind of be split between us. I'll start out with a little bit of a background in terms of some of the sample considerations and the thermal conductivity testing. And then I'll be throwing it over to Matt to take us through a little bit more application-focused background and some measurement results. So getting started here today, when I was going through the kind of preparation for today's webinar, started a few weeks ago, notice this recent, I'd say, announcement. As of July 1st of this year, there is changes to the essentially the duration to which no fire, no explosion, related to thermal runaway can occur in these different battery systems. What previously was a 2 to 5 minute window now has to last up to 2 hours. So there's still some interesting changes going on in the landscape. Of course, EVs have been on the market for years now, but we're seeing some of these just different regulatory requirements continuing to change. And of course, this will have a bearing on the different thermal management components inside of these battery systems. And specifically, when we're looking really at, who is this going to impact? Well, everything from the folks developing the packs, the thermal engineers at that level, the adhesive and polymer formulators. So, kind of akin to what Matt will and Matt's role and what their company does. So the people developing these samples and materials, and then just general testing, QA, and analysis labs as well, being able to, of course, measure these materials' properties to help quantify the performance to hit these thresholds that are being set. So again, today's conversation will focus largely on the EV space, the thermal interface materials, but specifically taking a look at some of these adhesives. So just as a quick agenda, as I kind of mentioned earlier, I will be kind of getting us going with some different things to keep in mind as you're going to do these types of measurements. I'll introduce our Trident instrument, go over a little bit of some testing details as it relates to adhesive films, and then I'll be throwing it over to Matt from Adhesives Research to basically cap off the second half of the presentation and wrapping everything up with that Q&A. So starting out, just a few important aspects I'd like to flag here when it comes to the thermal conductivity testing side of things. Starting very high level here, one of the fundamental considerations, especially when we look at transient-based approaches to measurement, your sample size, the resulting probing depth requirement, if that's a new term for folks, this is essentially what largely sets the sample size requirements, oftentimes relating to both the thickness as well as the diameter. Different methods will have different considerations here, related to one, the geometry and the style of the sensor, but then two, your testing durations, your evaluated volumes, again, that probing depth, how much of that material is actually being, let's say, sensed by the measurement, can play a significant role. And basic bulk style measurements are essentially set such that heat pulse is contained within the body of your material. Often you're dealing with potentially puck style or blocks shaped samples, some of these TIMs that are kind of cured in, the millimeter size range. However, in today's discussion, especially where we're talking about some of these adhesives, we need to look at it from the perspective of really testing thinner samples. So really, sub 1 millimeter thick. And This can introduce some challenges compared to just your more simplistic bulk style measurement. When we're dealing with samples that might be in, micron range thickness, we have to look at how we go about testing them. One solution is essentially taking those individual films or layers of sample, stacking them up, and essentially forming a bulk sized sample for measurement. This is one workaround. What we've done here in the past. I know many groups will opt for this depending, again, on what method constraints they're dealing with. And in many cases, this works quite well. This is just an example data set of some work that we did previously with the group, kind of testing their samples, measured versus expected, doing this stacking style approach. And it can work out quite well. We do have a full kind of application write-up on this specific use case. This is actually using our MTPS method, but it is certainly an option that exists. But it's not always, let's say, possible or practical to do so. Again, this is where it comes into the specific samples that you're dealing with. For example, if you're really on the low end of that micron range, well, to achieve a millimeter, maybe a couple millimeter thick sample, this could require up to 80 or even higher, like a large amount of layers, a lot of stacking. This is just, again, it's not practical, it's tedious to do. I can tell you I've done a measurement of this type in the past. It really, it's not what I would say typically the best way to go about doing it. But it is, again, possible if you have the patience to do so. But sometimes it's just really not possible. One sample type, just as an example here, like metals or these higher conductivity materials, often will have a high thermal contact resistance. So stacking them isn't really going to be a viable option here because you're going to get a significant bias introduced in between your layers. And this is actually like the fundamental basis of why thermal interface materials are needed. Because when we look at some of these exceptionally highly conductive, heat dissipating components in electronics, your let's say the CPU and like the heat sink that's attached to it. These are both conductive metals, but the reason that TIMs are used is to bridge those gaps to reduce that inherent contact resistance. So if you're looking to measure the thermal properties of some of these materials, stacking is sometimes not possible based on the type of sample, the surface conditions that you're dealing with. But even if you're dealing with something softer, maybe there's not an inherent high contact resistance at like the base interface. The process of actually layering the sample can also result in some similar issues in that if you get these imperfections or gaps forming between those layers, again, similarly, you're going to introduce a bias to the measurement. You're artificially changing that, what's actually going to transfer through the body of the system. And oftentimes this will result in a negative bias. So your values will come out lower than they actually should be. And this will have some bearing in not only the testing of the materials, like how you go about prepping them and stacking them up, but as I was chatting with Matt about this, and some of the development just in the manufacturing side, some of these processes take different layers and actually work very, very hard to ensure that if the materials themselves are actually fundamentally being formed through this layering process, that this is mitigated as much as possible. So again, there are some challenges here in treating a thinner sample as a bulk style material. And just wanted to kind of set that basis here because it'll detail a little bit of what we're going to go over and specifically how we did the measurements on the samples in question in this presentation. But before we go there, I thought I'd just take a pause at this point, and get maybe some feedback from the audience here. What are the typical sample thicknesses that you're dealing with of your materials? My colleague Carter will be posting the poll here in the chat here shortly. So give folks maybe 10, 20 seconds, if you wouldn't mind, just giving us some information on specifically the class of materials that you're dealing with, maybe help inform some discussion later on. Seeing some answers come in here. I'll give it maybe another few seconds. All right, I'll go ahead and end the poll at this point. Thank you for the folks that took the time to answer there. I'll share the results on screen just so we can take a look here. So yeah, quite a big spread. Okay, most folks seem to be dealing with that 10 to 100 micron thickness range, but of course spread across here. So again, this kind of just echoes the point, looking at that 10 to 100 micron range, to get the lower end of that thickness stacked up to a bulk size format. Again, tedious, time consuming. There are other options that exist out there. So this is what we'll start to go into here shortly. So thank you everyone for your participation in that. I'll stop sharing there. But yeah, moving forward here, at this point, we've talked about the samples, some of the challenges. Want to introduce our Trident instrument for the measurement of thermal conductivity. So C-Therm, if you're unfamiliar, we focus on the transient class of thermal conductivity instrumentation, a world leader in this space, specializing in non-destructive thermal analysis solutions. Our core instrument is called Trident. This is the system that was used and that we're featuring here today, and what was used to actually collect some of the data in today's presentation. But again, this is a modular platform. It brings together 4 different methods, each with their own sample size requirements, thermal conductivity range specifications, etc. Oftentimes, really, what we advocate for here is to choose the method that is going to really best suit your samples and testing needs, and not trying to just brute force fix a sample to a method it maybe isn't entirely intended for. And that idea is really embodied in this quote here from Abraham Maslow. It's one that we really find captures the spirit of Trident. When all you have is a hammer, everything looks like a nail. So again, just that whole idea of really trying to force a method on something it maybe really isn't designed for, being able to pivot into the tool, we'll call it, that is most appropriate here. Having that toolbox style approach really does ultimately result in better data, easier testing, and just an all-around time saver at the end of the day. So we're not going to go into all the methods on the Trident system here today, but for folks that are interested, we did publish quite recently, a little over a year ago now, an update to our method selection guide. This is available as a free resource download. Really goes over all of the transient methods that we offer on Trident, as well as other methods that are available in industry, like some of the more traditional steady state options and other transient methods that you can get access to. So if you're new to thermal conductivity, or maybe you've been in this space a while, but you want to kind of read up on kind of what there exists out there as options, this is a great resource to take a look at. All right. So coming to the crux of the specific samples here today, the adhesive films. Wanted to go over and give a little bit, basically giving a little bit of the setup to explain how these samples are tested, what our recommended option would be to avoid those bulk style prep requirements. And again, this will give a little bit of context to some of the information that Matt will be presenting later on. So one of the methods on Trident, and the one that we're going to focus on here, is the TPS, or transient plane source. So you can see a picture of the sensor here. This is a double-sided sensor, comes in some varying sensor sizes, but it's very thin, flexible. And in terms of its functionality, there are different modes of operation, or different utilities, as we describe them, that you can get access to. The base function of the TPS is referred to as bulk. And again, kind of similar in requirements here, kind of that probing depth consideration, the sample size being in the millimeter size range. Your sensor here will be essentially what's dictating your sample size requirements. General rule of thumb is your material diameter scales 2.5 times the diameter of the sensor that is chosen, with a thickness scaling 1 to 1. But again, in terms of the adhesive films, the bulk utility wouldn't really be the core focus, but it is, I'd say, your starting point as a basic functionality. What is going to be really more appropriate in this case is the TPS Thin Films Utility. And this is just a little graphic demonstrating this, essentially the testing process of a TPS Thin Films measurement. It's essentially a 3-point test that is done. You have your standard TPS sensor with a conductive backing material. This is actually part of the initial test or measurement that is performed, essentially taking a blank. You can view it as like a blank or a baseline measurement. And then you will essentially repeat the testing here with that same conductive backing in the sensor, but now with a layer of that film added onto the top side and to the bottom side of the sensor in that stack. This is repeated one final time, so you have 3 separate measurements that are then used to quantify the thermal conductivity of that adhesive film or thin film or even coating. These are the kind of the core thinner format samples that this utility really accelerates at. Now, the ISO standard is 1. There's also an ASTM, but ISO 22007-2 is one standard that does detail quite a bit of information on the TPS thin film. So just put a little excerpt here, talking about, the requirement for that conductive backing material, kind of testing different thicknesses. I will say, if you're interested in the TPS method as an option for your material analysis, the ISO is a good starting point to kind of get informed on what the system is designed for, what those different utilities offer. But I wanted to show you here, this is just an example of what the Trident software from C-Therm actually looks like when you're running a TPS thin films measurement. So as I said, it's a 3-point test, and you can see what you're essentially doing here is measuring that delta T, that change in temperature that occurs as a function of time. This is then plotted as against the thickness of the material. And we're essentially doing a linear regression through this step process to quantify the conductivity. So this is the setup and kind of the approach that was used in the testing of the adhesive films that Matt will be going in to present here shortly. But we've also tested a variety of other materials, like different reference samples. We do have a variety of application notes on TPS and specifically the thin films utility that are available. Again, all of this is free resources through the website. And you can follow the QR codes on screen. But if you are looking to get more examples or more information on this type of testing, we're certainly happy to provide that. But at this point, I'm going to hand it over to Matt from Adhesives Research, again, to take us through some background on more of the application space, EV systems, thermal management, and again, specifically go into the adhesives results. And I will say, I believe Carter will also be posting in the chat. We did a collaborative application highlight on this work. So again, some of the content that's going to be presented here is available in a write-up. So you're certainly happy to take a look at that.
All right. Well, thank you, Aria. That was a great introduction. Really appreciate all the background information that we're going to use to help describe some of the adhesive systems that we tested for EV battery thermal management materials. And so as Aria said, my name is Matt. I'm a team member here at Adhesives Research, where I am a product development chemist in our electronics group. So who Adhesives Research is, we are a adhesive developer and manufacturing company located in Glen Rock, Pennsylvania, which for those of you that aren't familiar is about 2 hours west of Philadelphia. We've been around for about 65 years, and we pride ourselves in providing differentiated technologies, working with customers closely on custom solutions, and rapidly prototyping and scaling up materials for those customers. I'm a member of our innovation group. So our innovation group is roughly 40 scientists and engineers who work on the custom development and manufacturing of adhesive polymers and formulations. And for this particular application here, it's important that we have significant analytical equipment to allow us to rapidly iterate and help solve complex problems. In-house, we have significant scaling of analytical equipment, but we also work with other groups like C-Therm to do specific testing on our materials when it's practical for the types of applications that we're going to be looking into. As I mentioned, I'm a member of our electronics team. This spans a large number of market segments. A couple of market segments that I won't talk about today, but that we do work with significantly is the consumer electronics, in particular optically clear adhesives for digital displays such as phone screens or e-readers, as well as the renewable energies market, think solar in this case, where adhesives are used both for charge collection as well as protection from the elements in the form of encapsulants. Today, I'm going to talk specifically about our EV and e-mobility adhesive segment line, and in particular, the materials that are used to help with thermal management in these systems. So EV batteries and e-mobility systems in general actually can use a large number of adhesive and tape solutions for different parts of the applications. The two that I'll highlight today are thermal interface materials, which are conductive adhesives used for ambient cooling, as well as thermal runaway protection adhesives, which are adhesives that are used to help prevent catastrophic thermal propagation in EV systems. There are other locations where tapes and adhesives are used. In particular, I've highlighted a couple here. Dielectric tapes are often used as wraps to help prevent electrical charge from jumping between different components in EV batteries and electric vehicles. Encapsulants are also used heavily. A lot of the sensitive components within the EV batteries are moisture sensitive, or in other areas would react with water or the air, and so adhesives can be used to help prevent ingress of moisture or air into these systems. And then conductive adhesives are also used. Bus bar applications allow for charge mobility throughout the EV battery itself. There also are examples where conductive adhesives are actually used within electric battery cells themselves to provide improved interface conductivity within these systems. But today I'm going to highlight specifically the thermal interface and thermal runaway protection adhesives and the work that we did with C-Therm to develop a new thermal runaway protection material for EV batteries. And so as I already mentioned, is very prevalent currently in the news. The EV battery market is rapidly expanding. So the graph on the left I have here shows the increase in expected market share of EV batteries as a function of time over the next 5 years. You can see that from 2025 to 2020 to 2030, we have more than a doubling of the expected market value of these EV batteries. This is a great opportunity for those that are working with EV battery systems to help provide new solutions, but it also means that issues that we have currently with potential risks for consumer safety in these EV batteries need to be addressed quickly and in a way that is easily scalable. And then just to kind of orient everybody on what a battery cell actually looks like within these systems, I just have a diagram here on the right. So a battery cell effectively consists of four things. You have a cathode and anode, which is where your charge will build up and then dissipate from. And then between them, you have an electrolyte, which allows the ions to move through when the system is charging and discharging. And then in particular interest for our conversation today, the separator. This is actually there to help prevent rapid transmission of energy between the two sides of the cell. And failure in the separator can cause catastrophic failure in the battery system itself. This can happen through either an internal damage to the system through something like dendritic growth, or through an external puncture to the cell, like a nail puncture. And so if this were to occur, the cell can then rapidly heat up. And if multiple cells heat up, this can lead into what we call thermal runaway. Wanted to highlight a little bit more about what the inside of an EV battery would look like and talk about the different levels in these systems. So I just showed what we call an EV cell. These battery cells are relatively small compared to the entire EV battery. Multiple cells are put together into what are called modules. These modules have components within them that help with thermal and pressure management. So as the cells charge and discharge, they can expand and contract. And so there are pressure management materials within these modules, often foams, which help keep the overall volume of the cells consistent. And then there are thermal management materials as well. These are things that are often insulative and help prevent heat from being transmitted between cells in the event of a catastrophic failure. The modules themselves are then built into what are called packs, and this entire pack system has all of the electrical components that allow the battery to charge and discharge, as well as some ambient cooling and other electronics. So here I'm highlighting three different areas where thermal management or thermal protection are used in these EV battery packs. The one that's maybe most obvious to anybody who's seen an EV battery is the cooling plates. These are often located at the top and bottom of the packs. These allow for passive cooling of the EV batteries during normal operation. So as heat is generated when the cells charge and discharge, and as the system goes through normal wear and tear, heat can then be wicked to the cooling plates, which allow for passive cooling during normal operation. Another thing that's used for standard operation are what are called potting compounds. These are used to both hold the cells in place within the modules. They're also generally thermal interface materials, which Aria mentioned earlier, really help improve thermal conductivity between metals or other highly conductive systems that allows for easy heat transport between them. These potting compounds or thermal interface materials are highly conductive for adhesives. They're often either two-part silicones or two-part epoxies that have a large amount of filler material in them, which allows for heat to be wicked away from the battery cells and ultimately to the cooling plates. And then most practical to what I'll be talking about today are thermal barriers. These are materials that are placed again between cells that help prevent heat from being transmitted during catastrophic failure in the cells. These are generally low thermal conductivity materials, such as aerogels or mica sheets. And the benefit here is that they can be in place while the cells are under normal operation, but when the system undergoes some sort of failure mode, they can help provide slow down of heat to allow for safe egress of the vehicles, which is incredibly important for consumer safety. And then thermal runaway, just to highlight exactly what this is. Generally, what can happen inside a cell if there's failure within a single battery cell is the neighboring cells will start to heat up rapidly. And if this happens too quickly, the entire system will fail in relatively catastrophic ways. I'm sure we've all seen examples of this in the news. It's often covered when an EV battery or an EV vehicle goes off. And this can, of course, result in loss of the vehicle, but in unfortunate cases, loss of life if the consumer is unable to exit the vehicle efficiently. And so what we wanted to look at were different ways to help provide passive systems within these EV batteries to allow for longer egress. And as was mentioned at the top of this talk, there's been a recent movement to increase the amount of time that is allowed for consumers to exit the vehicle from a few minutes to up to 2 hours now. So we're working towards the development of adhesives that can help with that goal. And so just to highlight a couple of different areas within these EV battery modules where adhesives are used and how we are able to use our adhesives to help improve consumer safety. There's two main areas on the module level, again, where adhesives are used. The first I haven't mentioned yet, and it's actually an adhesive that has one function only. When you're actually designing and building the modules from individual cells, an acrylic adhesive, so usually a relatively inexpensive material, is used to help align the battery cells with each other before the system is placed under pressure, which these systems are always under some amount of pressure. So they're used for this one application, but then they sit ambiently between the cells for the remainder of the battery's life and really don't have a function following that. But this is actually an area where we saw an opportunity, and I'll talk a little bit more how we're working towards developing an adhesive that provides both this alignment function, but also provides some passive protection from the thermal events that can occur in these systems. And then, as I mentioned previously, thermal interface materials. These are high conductivity systems that are placed between the battery cells themselves that allow for wicking of heat during normal operation. So these thermal interface materials or potting compounds have very high filler levels. We're talking 60 or 70% by solids percentage, which allows for what's called a percolation network or easy transmission of heat between the two surfaces due to the high level of fillers that are in these potting compounds. And so these thermal interface materials really do well at allowing for passive heat dissipation during normal operation, but they can have some problematic effects during thermal runaway events due to this high thermal conductivity. And so to look at the difference between these thermal interface materials and some of the materials we've been developing for thermal runaway protection, we turned to C-Therm and in particular the Trident TPS system to try to help us understand how varying the filler level and the adhesive thickness can change both thermal conductivity and the ultimate performance in thermal runaway protection that these adhesives can provide. As was mentioned by Aria earlier, this can be difficult when looking at thin film adhesives. And at the beginning of this particular project, we did exactly what he talked about. We were layering up adhesives constantly to get very thick films so we could measure them, which, while it worked on the short term, was relatively impractical for rapid development of materials, and also induced a lot of unnecessary interfacial effects that we, in the long term, determined were providing negative value to us. And so, in conjunction with the C-Therm team, we looked more about how we could look with our materials and test natively made thin film materials and see how consistently we could get measurements on them in terms of the thermal conductivity. These direct measurements give us a twofold advantage. They allow us to rapidly iterate, so materials can be made and tested almost immediately without having to take the time to stack materials. But it also really gives us confidence that we're not inducing interfacial effects, which can really be detrimental to our long-term goals. And so on the right, I'm showing a graph here with two different versions of the thermal runaway protection adhesive that I'll talk about here in a moment. But you can see that at both 75 microns and 150 microns, using the TPS system, we can get very similar thermal conductivities. This is then the intrinsic thermal conductivity of this material. It allows us to have confidence that we can measure these systems and iterate rapidly to help improve product development. And so tying this all together then, in terms of the materials that we were making for thermal runaway protection, these adhesives that we were developing are intended to go in place of the acrylic adhesives that are often used for alignment in EV batteries. So they would be placed between different battery cells in terms of making the battery modules. And so here you can see kind of what the overall stack would look like. You'd have the individual cells that are separated by both an adhesive, which again formally would be an alignment adhesive, but in this case is a value-added thermal runaway protection adhesive. Then there's also often a pressure management material in these systems that helps keep the battery with the overall consistent volume during charging and discharging of battery cells, which can change the volume of those battery cells during normal processing. And so we wanted to test different adhesives in conjunction with these pressure management foams and determine optimal levels of fillers to help allow for thermal runaway delay without having high enough filler levels that you'd actually end up with thermal conductivity similar to a thermal interface material, which we know can be detrimental under thermal runaway conditions. And so on the right side, you can see the different levels of thermal conductivity that we were measuring for our thermal runaway protection adhesive, as well as a model thermal interface material using a similar acrylic. This material has a much higher filler level, matching what's often used in the thermal interface materials, the potting compounds. These materials can have thermal conductivities anywhere from 4 to 10 watts per meter Kelvin, and this material is very much in that range. You can see that our thermal runaway protection adhesive which has a much lower filler level to prevent that percolation network from forming. Has a thermal conductivity that's in line with the unfilled acrylics that are often used in these battery systems. This is, we think, a good thing because it allows us to have a lot of fillers to help with thermal runaway protection, but not reach that percolation threshold, which again, under thermal runaway can be a detrimental effect. And then measuring the actual thermal runaway delay of these adhesives with these pressure management foams. This test here effectively takes these stacks and places them on high temperature hot plates and then measures the temperature transmission through the stack as a function of time. So starting on the left, the pressure management foam with only the construction adhesive on it, you can see relatively quickly heats up to the temperature that we've dictated is the limit to where we would see a thermal propagation to the next battery cell. In yellow in the center is the thermal interface acrylic adhesive. This material does have fillers which help prevent the transfer of heat between the two cells, but due to the high level of fillers, there is ultimately transport at a level that is unacceptable in this application. And so the thermal runaway protection adhesive provides kind of a best of both worlds scenario where you have enough fillers to provide a significant thermal runaway delay, but not so many that you have good percolation network through the adhesive. And so you end up with a low thermal conductivity, which allows you to have a much better thermal runaway delay overall. And so this material, along with its stacking in the battery system, can help improve consumer safety and improve the thermal runaway delay in these systems. And so just a few takeaways before I spin this back over to Aria. We're hoping we can show that pressure-sensitive adhesives can provide value-added roles in battery modules and not just the initial construction adhesive role that it had played up to this point. Using the TPS system, we were able to rapidly iterate and work to develop the best possible adhesive for this application. And the accurate measurements that we got from this really helped us have confidence in the results that we were seeing and correlate it well with that burn test data that I showed on a previous slide. And overall, the ability to reduce thermal runaway is a big goal in the next few years to help improve consumer safety as we're rolling out more and more EV batteries and the regulations for these systems are becoming more and more stringent. And so overall, I'd be happy to take any questions in a few moments. If you'd like to learn more about adhesives research and our electric vehicle adhesive market, please take a scan of the QR code on the screen right now. My information is also here. Please feel free to reach out via email or phone at any time, and I'd be happy to talk about any of this further. And with that, I'm going to spin this back over to Aria to send us out today.
Awesome. Thank you very much, Matt. Yeah, folks, just going to be wrapping things up here shortly. Just going to couple little outro slides. But before we go to that, I just wanted to do one last poll here, actually, with the folks on the line. Interested to know how are you currently validating your material performance? I saw like the poll earlier talked about quite a range of thicknesses, so that we can see that. But is this something that you are currently doing in-house? Is this through third-party labs? Or are you simply relying on the technical data sheets and kind of using that as your basis of performance? I've asked this question in a few different application talks, and the answers do vary a bit, but just curious how you folks that are dealing with these adhesives are currently approaching this aspect. So yeah, I'll let this poll go for maybe another few seconds here. All right, I'll go ahead and stop it now at this point. And yeah, interestingly, so like I said, I've asked this same question a few different areas of application, and in-house testing, I would argue is, of course, to Matt's point, being able to rapidly iterate, get feedback quicker, knowing how to operate the measurements and get useful data is really important. And I see that's, I think, what the majority of folks are doing here. Some third-party labs, technical data sheets only. Yeah, I would say for the folks, won't name names, of course, for the answers, they're anonymous. But for the technical data sheet only, that is like I said, we have different application write-ups. We've seen in some cases there where TDS may not always align with reality. Certainly it's a good basis to begin from, but testing directly, I would say, is of course going to be the safest approach here. But to everyone taking the time to answer, thank you very much. Stop sharing that. All right. And like I said, just kind of going into the outro here, talking about third-party testing, if you are a group that is currently working with thermal conductivity, conductive or insulative materials, here at C-Therm, we do offer full testing services through our contract testing division, thermal analysis labs. Of course, all of the Trident methods that we have are available through our testing division. Excuse me, but also other instrumentation, other properties, like a variety of DSC, TGA, STA options as well. So certainly happy to support the groups that are looking for options that exist out there in form of testing services. Did want to make note, we didn't really feature this in today's content, but we are partnered with ZFW for their line of TIM testers as well as high temperature heat flow meter systems. This opens the doors to some different sample types, different information on the materials. So again, if this was of interest as an option or a service, or bringing that in-house for both the transient and steady state options, definitely feel free to reach out to us. We'd be happy to talk about both avenues. And with that being said, now brings us essentially to the end of today's session. Once again, I'd like to thank Matt for taking us through his content here today. And it was just say it was great working with you here over the last little while on the samples and the content that we got put together. So thank you for the opportunity there. And also thank you to the audience for the groups that took the time to join.